Welcome back to Stack Lessons. 20 questions today, focused on inference table failure modes, AI search mechanics, and AI gateway guardrails. 10 seconds per question on the timer, but pause whenever you want. Let's go. Time for another one. Question 1. Small wording, big difference. A generative AI engineer at Northwind is creating an AI search index for a new product search feature. Their Unity Catalog workspace uses a catalog named products_catalog and a schema named search. Which index name correctly follows the 3-level Unity Catalog namespace convention? Select one. Review the answer choices on screen. The correct answer is option A. The delimiter tells Unity Catalog how to parse the name. Unity Catalog uses a 3-level delimited namespace in the form catalog.schema.object for all governed resources including AI search indexes, delta tables, and registered models. The / delimiter is path notation used in file systems and object storage, not the Unity Catalog namespace separator. Reversing catalog and schema produces a reference to a non-existent catalog called search, which would fail at index creation time. Including the workspace as the first namespace level is incorrect. The workspace is not part of the 3-level Unity Catalog hierarchy. Time for another one. Question 2. Let the constraints drive the choice. A generative AI engineer at Southgate Analytics is building a RAG application for a financial analyst team. The system must answer 2 categories of questions: narrative questions about regulatory filings stored as PDFs, and quantitative questions requiring precise figures from a relational transaction database. Both question types must be handled through a single conversational interface. Which architecture best supports this requirement? Select one. Review the answer choices on screen. The correct answer is option C. 2 data types need 2 retrieval strategies, not one. A RAG application handling both unstructured documents and structured relational data requires routing queries to the appropriate retrieval mechanism. PDF regulatory filings are best served by a vector store with semantic similarity search, while precise quantitative figures from a transaction database require SQL queries that return exact values rather than approximate semantic matches. Routing based on question type ensures each query uses the retrieval method that matches the data format and precision requirement. Embedding database tables into a vector store loses the structural precision of tabular data. Semantic retrieval approximates rather than computes exact financial figures, making it unsuitable for quantitative queries. Converting database records to text summaries and embedding them degrades numerical precision and creates a large stale index that must be regenerated whenever transactional data changes. A fixed retrieval chain that only queries PDF content cannot return precise quantitative figures from the database, and relying on the LLM to infer missing numbers introduces hallucination risk for financial data. Ready. Question 3. Watch for must, most, least, or except. A generative AI engineer at Ridgeline AI is registering a fraud detection model to Unity Catalog using MLflow 3. The model will live in a catalog called ops_prod under a schema called security_ML with the name fraud_classifier. Which argument should they pass as the registered_model_name parameter when calling MLflow.register_model? Select one. Review the answer choices on screen. The correct answer is option C. Unity Catalog requires the full 3-part path here too. Unity Catalog uses a 3-level delimited namespace for every managed object, including registered models. The required format is catalog.schema.model_name, so ops_prod.security_ml.fraud_classifier is the correct argument. Providing only the model name fraud_classifier without catalog and schema qualifiers either resolves to the legacy workspace level registry or fails outright when MLflow is configured with the Databricks UC registry URI, which is the default in MLflow 3. // are not valid namespace separators in Unity catalog syntax and will cause the registration call to fail with an error. Colons are equally invalid as namespace delimiters for Unity catalog objects and will produce the same failure. Let us switch gears. Question 4. The obvious answer may be bait. A generative AI engineer at Sycamore Search is building a legal document discovery tool using hybrid keyword and semantic search. The downstream aggregation pipeline requires at least 500 matching documents per query. During load testing, the engineer observes that no query ever returns more than 200 results, regardless of how many documents match the criteria. What is the cause of this ceiling? Select 1. Review the answer choices on screen. The correct answer is option C. Hybrid queries hit a wall that ANN queries don't. Databricks AI Search enforces different result count ceilings depending on the query type. Approximate nearest neighbor queries support up to 10,000 results, while hybrid search queries and full text search queries are capped at a hard platform limit of 200 results per query. This ceiling cannot be raised through configuration and is independent of the number of matching documents in the index. The engineer's requirement of 500 results per query cannot be satisfied with a single hybrid search call. The retrieval strategy or downstream aggregation approach must be redesigned to work within the 200 result constraint. The maximum index size of a standard endpoint is measured in total vectors stored, not in results per query. The RRF_Purim coefficient affects how scores are merged during fusion, but does not impose a numerical cap on the result count. CDF synchronization lag would produce missing documents across all query types, not an exact ceiling of 200. This one catches a lot of people. The result ceiling in AI search is not what you'd expect. Imagine you're the Sycamore Search engineer. Your index has 10,000 legal documents. You ask for 1,000 results from a hybrid query. You get back exactly 200 every time. That ceiling is not a config value you set wrong. It is a hard platform limit in Databricks AI Search. Hybrid queries hit 200, and so does full text search. Vector-only queries can return up to 10,000 results, but the moment you add keyword search, that ceiling drops to 200. The RRF parameter, the score blending formula, only changes how results are ranked, not how many come back. Index size is a separate axis entirely. You can store a billion vectors and still only retrieve 200 per hybrid query. If you need 500 results, you need to rethink the query strategy. Ready? Question 5. Read it carefully. A generative AI engineer at Tapestry Media is building a content policy enforcement system that analyzes user-submitted thumbnail images and short preview video clips to detect guideline violations. The engineer wants a single foundation model API model call that natively ingests both modalities without a separate pre-processing pipeline. Which model should they select? Select 1. Review the answer choices on screen. The correct answer is option C. Only one model here handles video natively in FMA. Gemini 2.5 Flash supports all 4 input modalities: text, image, video, and audio through the Foundation Model API. making it capable of natively ingesting both thumbnail images and video clips in a single model call without any additional pre-processing pipeline. This native video support is the decisive differentiator that allows a single model call to process both input types for policy analysis. Claude Sonnet 4 supports text and image inputs within the Foundation Model API, but does not support video as an input modality, making it incapable of natively ingesting video clips. Llama 4 Maverick similarly supports text and image inputs only, and cannot process video content without a separate frame extraction step that routes the workload outside the model's native capabilities. BGE Large is an embedding model that produces vector representations for retrieval and similarity search. It cannot interpret visual or video content, cannot detect policy violations, and cannot generate structured text output of any kind. First 5 questions established Unity catalogs. Delimited namespace rules, RAG routing by data type, and Gemini 2.5 Flash as the only FMA model with native video ingestion. Keep your focus here. Question 6. Reason from the scenario. A generative AI engineer at a Datum Corp has configured an inference table on a production model serving endpoint to capture all requests and responses for audit purposes. After 4 weeks of reliable operation, the compliance team reports that the inference table has completely stopped receiving new entries. Which scenario is the most likely cause? Select one. Review the answer choices on screen. The correct answer is option D. Logging stopped completely. That rules out sampling fraction changes. Inference tables stop logging entirely if the underlying table schema is changed, the table name is changed, or the table is deleted. A data engineer renaming the inference table in Unity Catalog breaks the binding between the endpoint and its log destination, causing all subsequent entries to silently fail to be recorded. Exceeding the 128 concurrent request limit can cause throttling on individual requests, but does not disable the inference table for future requests once load normalizes. Reducing the sampling underscore fraction from 1.0 to 0.8 means 80% of requests are still captured, reducing volume but not stopping logging entirely. Payloads exceeding 10 MB, not 1 MB, are excluded from logging, but payloads below that threshold continue to be captured normally regardless. Keep your focus here. Careful on question 7. This one has a trap. A generative AI engineer's upstream embedding pipeline normalizes all document vectors to unit length before writing them to a delta table. The team needs to confirm that Databricks AI Search can support cosine similarity semantics for a document deduplication system. Which statement accurately describes how cosine similarity is achieved in Databricks AI Search? Select one. Review the answer choices on screen. The correct answer is option D. Unit normalizing embeddings before indexing changes how distance works. Databricks AI Search uses the hierarchical navigable small world algorithm with L2, Euclidean, distance as its internal metric. For unit normalized vectors, L2 distance and cosine distance are mathematically equivalent and produce identical rankings because the magnitude of all vectors is 1. Since the engineer's pipeline already normalizes embeddings to unit length before storage, the L2-based index inherently delivers cosine similarity behavior with no additional configuration required. There is no distance underscore metric parameter in the AI Search Index Creation API. Cosine similarity is effectively supported through normalization rather than a configurable metric switch. The index type, delta sync versus direct access, does not affect the underlying distance metric used by the HNSW algorithm. Let's slow down here. The cosine versus L2 distance question is a clever math trick. Imagine you're storing 50,000 product descriptions as embeddings and need to find near duplicates. You know cosine similarity is the right tool, but Databricks AI Search uses L2, Euclidean, distance internally. So are you stuck? Here's the trick. When every vector has length exactly 1, L2 rankings match cosine rankings perfectly. That's just math. No extra config needed. Your pipeline already normalizes to unit length before writing to delta, so cosine behavior is already baked in. There's no distance _ metric parameter to pass. The exam rewards knowing pre-normalization is the whole trick, not a missing flag. Keep your focus here. Let's get into question 8. A startup is prototyping a customer support chatbot with low, unpredictable traffic before a planned public launch. The team expects usage to grow substantially once the product ships. Which combination of foundation model API pricing strategies should they follow? Select one. Review the answer choices on screen. The correct answer is option A. Match the pricing model to where traffic actually is. Pay-per-token pricing is the recommended starting point because it requires no capacity commitment and scales to 0 when idle, making it well-suited for prototyping under low or unpredictable traffic. Once the application reaches production with sustained, predictable volume, provisioned throughput becomes the right choice because it delivers consistent latency guarantees and is more cost-effective at high throughput. Starting with provisioned throughput during prototyping wastes spend on reserved capacity that sits unused during the low traffic period. Continuing with pay per token into high-volume production is not recommended because provisioned throughput provides better price efficiency and stronger SLA guarantees at scale. Provisioned throughput for both phases incurs unnecessary reserved capacity costs well before the application has earned them. All right, question 9. Anchor on the exact workload. A generative AI engineer Advantage Analytics enabled inference tables on a provisioned throughput model serving endpoint several weeks ago and confirmed that request and response logs were being captured correctly. The team now reports that no new records have appeared in the inference table for the past 24 hours, even though endpoint traffic metrics confirm normal request volumes. The engineer has made no changes to the model or serving configuration. Which change is the most likely cause of the logging gap? Select one. Review the answer choices on screen. The correct answer is option C. Schema changes after association silently break inference table writes. Inference tables stop logging when the schema of the underlying delta table is changed after the table was created and associated with the endpoint. If a team member added, removed, or renamed a column, the endpoint can no longer write records that conform to the original expected schema, causing all subsequent logging to silently halt. The 128 concurrent request limit governs how many requests can be processed simultaneously and may result in queuing or rejections under extreme load, but it does not pause inference table logging and would manifest as visible endpoint errors rather than a silent 24-hour gap in records. The 10 MB payload limit causes individual oversized requests to be excluded from the log, but it would not silence all logging for an entire day unless every single request exceeded that size, which is extremely unlikely for normal endpoint traffic. Delta tables do not impose a fixed row count ceiling that stops ingestion. They grow continuously without a built-in size-based logging pause. Okay, question 10. Translate the story into requirements. A generative AI engineer at Wexford Consulting is building a system that matches new client project requirements, written descriptions of 3 to 5 sentences each, against a database of thousands of consultant profiles listing skills, experience, and domain expertise. The system must generate an embedding for each incoming requirement and retrieve the most relevant profiles. Which entities should be embedded and stored in the AI search vector index? Select one. Review the answer choices on screen. The correct answer is option C. Stable corpus belongs in the index. Transient queries stay outside. The core architectural principle for vector store design is to embed the stable, numerous corpus into the index and use the transient, fewer items as queries at retrieval time. Consultant profiles are the stable corpus. They exist in large quantities, are updated infrequently, and represent the searchable knowledge base the system reasons over. Project requirements are the transient queries. They arrive one at a time, are short-lived, and function as search inputs rather than indexed content. Embedding profiles into the vector store and using each new project requirement as the query follows this principle and enables efficient, scalable matching without rebuilding the index as new requirements arrive. Embedding project requirements into the vector store and querying with consultant profiles reverses the corpus and query roles, resulting in a constantly changing index that must be rebuilt with every new project and producing semantically inverted retrieval. Maintaining bidirectional vector stores doubles infrastructure complexity without improving matching quality for this fundamentally asymmetric use case. Keyword-only BM25 search misses the semantic relationships between related but non-identical terminology in unstructured skills and requirements text. A consultant with experience in machine learning may not lexically match a project requiring artificial intelligence without semantic understanding. 6 through 10 revealed inference tables fail silently on rename or schema change. Hybrid AI search hard caps at 200 results, and that the corpus belongs in the index while queries stay transient. Okay, question 11 is up. A generative AI engineer at Lakewood Healthcare is building an internal question-answering assistant that should respond naturally to employee questions without any additional training. The team wants to deploy DBRX immediately without a fine-tuning phase. Which DBRX variant should they choose? Select one. Review the answer choices on screen. The correct answer is option D. Instruct is the deployment-ready variant, no extra training needed. DBRX Instruct is the instruction-tuned variant specifically designed for following natural language instructions and engaging in direct question answering without additional training. It is the appropriate choice when deploying immediately for conversational use. DBRX Base is a pre-trained auto-completion model intended as a starting point for fine-tuning, not for direct deployment in an instruction-following application, because it generates text continuations rather than structured answers. Its autocomplete architecture is precisely the characteristic that makes it unsuitable for conversational deployment without additional fine-tuning. Fine-tuning DBRX Instruct on domain examples can improve performance on specialized content, but it is not required before initial deployment. DBRX Instruct already follows instructions effectively out of the box. Okay, question 12. Separate fact from assumption. A machine learning team at Westbrook AI has been iterating on their LLM pipeline using MLflow logged models, accumulating evaluation metrics, parameter configurations, and request traces throughout development. They have identified the best performing iteration and want all of its captured performance data to appear automatically on the Unity Catalog model version page for governance review. What action achieves this? Select one. Review the answer choices on screen. The correct answer is option D. Registering the logged model carries all captured data automatically. When a logged model is promoted to a Unity Catalog model version, all performance data including metrics, parameters, and execution traces captured during development automatically becomes visible on the UC model version page. This promotion step preserves the full development history without requiring any re-logging or re-execution. Manually re-logging metrics using mlflow.log_metrics is unnecessary. and risks losing traced data that is tied directly to the logged model's captured execution context. Exporting artifacts to DBFS and importing them manually severs the traceability link between the artifact and its captured performance metadata, defeating the purpose of using logged models throughout development. Rerunning the full pipeline generates entirely new data rather than preserving the validated results tied to the specific iteration the team already selected. This one trips up a lot of people. Let's walk through what actually happens when you register a model. Imagine you've run 50 evaluation loops on your LLM pipeline. Every metric, trace, and config you logged got pinned to a specific logged model. Now you've picked the winner. The exam asks, how do you get that data onto the Unity Catalog model version page? Here's the trap. 3 wrong answers want you to relog or rerun. Don't. Just register the logged model to Unity Catalog. That single call promotes it to a model version. The UC page is a view over data already captured. Everything shows up automatically. The punchline? Registration is promotion, not migration. Next up, question 13. Picture the scenario first. A generative AI engineer at Moorgate Systems has an inference table enabled on a production model serving endpoint. After a maintenance window in which the team renamed the Unity Catalog table to align with a new naming convention, they discover that no requests have been logged since the rename. What is the cause of this behavior? And what must be done to restore logging? Select one. Review the answer choices on screen. The correct answer is option A. The rename broke the endpoint reference. Auto-resumption never happens. Inference tables stop logging permanently if the configured table name is changed, the table schema is altered, or the table is deleted. Renaming the Unity Catalog table severs the endpoint's internal reference to its logging destination. To restore logging, the engineer must reconfigure the inference table setting on the endpoint, after which Databricks Auto creates a new table at the specified name. There is no automatic resumption after a rename because the endpoint's stored configuration continues to reference the original table identifier. Altering column definitions does not reconnect a renamed table to the endpoint. Inference tables write to a Unity Catalog Delta table, not to a DBFS path, so no records are recoverable from DBFS. Next up, question 14. The condition is doing work. A generative AI engineer at Northwind Legal built a RAG application that answers questions about contracts by retrieving relevant contract clauses as context. The team is concerned that generated answers sometimes introduce information not present in the retrieved clauses. They want to use MLflow's built-in LLM judge metrics to automatically flag these cases at scale. Which built-in MLflow judge metric should they apply? Select one. Review the answer choices on screen. The correct answer is option C. Faithfulness measures one thing. Does the output stay in context? Faithfulness is specifically designed to measure how factually consistent a generated output is with the provided context. A high faithfulness score means the answer stays within information present in the retrieved clauses, while a low score signals the model may be contradicting or ignoring the context and introducing content not grounded in the source, exactly the issue the team wants to detect. Answer_relevance evaluates whether the output is topically appropriate to the input question, but explicitly ignores context, so it cannot detect when an answer introduces hallucinated information absent from the retrieved documents. Answer_similarity compares the generated output against a labeled ground truth reference answer, which the team does not have for every contract query. Answer_correctness also requires labeled ground truth answers to measure factual accuracy, and is therefore unsuitable when the only available reference material is the retrieved context itself. Now, question 15. The wording is the clue. A generative AI engineer at Clearwater Medical is measuring retrieval quality for a clinical trial literature RAG application. For each query, Multiple relevant studies may exist in the corpus, and it is unacceptable to miss any of them, even if some marginally irrelevant papers are also returned alongside the relevant ones. Which retrieval metric should be used as the primary optimization target? Select one. Review the answer choices on screen. The correct answer is option C. The phrase "unacceptable to miss any" is your metric signal. Recall at K measures the fraction of all ground truth relevant documents in the corpus that appear within the top K retrieved results. When missing a relevant document is the primary failure mode, as in a clinical trial application where an omitted study could influence a medical decision, recall is the correct metric because it directly quantifies retrieval completeness across all relevant items. Precision at K measures the fraction of retrieved documents that are actually relevant, which penalizes returning irrelevant results but does not capture whether all relevant documents were found. NDCG at K evaluates the ranking quality of retrieved results and rewards highly relevant documents appearing near the top of the list. It does not specifically measure whether all relevant documents were retrieved. Mean reciprocal rank focuses on how quickly the first relevant result appears and is most useful when any single relevant document is sufficient, not when comprehensive coverage across all relevant results is the priority. This one trips up a lot of people. Let's nail the difference between recall and precision. Imagine you're a doctor searching for every clinical trial about a drug interaction. You'd rather get 20 papers, even if 5 are off topic, than miss one critical study. That's the core trade-off. Precision at K asks, how clean is my result list? It penalizes irrelevant results but doesn't know what you missed. Recall at K asks, did I find all of them? It counts how many known relevant papers appear in your top results. Say your corpus has 50 relevant studies. Precision at K doesn't care if you only surfaced 10 of them. Recall at K catches that gap immediately. When one missed paper could change a medical decision, recall wins. That's why precision sounds rigorous but measures the wrong thing here. Questions 11 through 15 reinforced DBRX Instruct for zero-shot deployment, MLflow logged model promotion auto-surfacing all metrics, and recall at K as the metric when missing any relevant document is unacceptable. Next up, let's get into question 16. A generative AI engineer at Fairmont Data Services is building an LLM-powered HR assistant on Databricks. Employees will ask benefits questions in free text, and the compliance team is concerned that employees may inadvertently include their social security numbers or personal email addresses in queries. Regulations require that this PII must not be forwarded to the LLM or stored in request logs. Which AI gateway feature should the engineer enable? Select one. Review the answer choices on screen. The correct answer is option C. PII detection transforms the payload before forwarding. Others don't. PII detection and redaction automatically identifies personally identifiable information, such as social security numbers, email addresses, and phone numbers within incoming requests and replaces them with placeholder tokens before the payload is forwarded to the LLM or written to any logs. This directly satisfies the compliance requirement by ensuring PII never leaves the platform in a recognizable form. Rate limiting controls request volume to prevent cost runaway and protect service availability, but it has no effect on the content of requests that do pass through. Safety filtering targets categories of harmful generated content such as hate speech, insults, sexual material, and violence. These are content governance controls that do not detect or redact structured personal information. Traffic tracking logs usage and attributes costs to users and teams for reporting, but it records rather than transforms payloads, so PII would still be present in those logs. Let us keep moving. Question 17. Look for the answer that fully satisfies it. A team at Carlton AI is building a legal document processing platform. One sub-team needs to fine-tune a foundation model on a proprietary corpus of case law before adapting it for downstream extraction tasks. A second sub-team needs to immediately deploy a model that can follow instructions such as extract all party names from this contract without any additional training. Which DBRX variants should the respective teams use? Select 2. Review the answer choices on screen. The correct answers are option A and option C. 2 roles, 2 variants. Fine-tuning needs the clean slate. DBRX Base is the pre-trained, autocomplete style variant of DBRX, whose weights capture broad pre-training knowledge without instruction following fine-tuning applied on top. This makes it the correct starting point for domain-specific fine-tuning, providing a clean foundation for adaptation to legal case law. DBRX Instruct is the variant explicitly fine-tuned to follow human instructions reliably, making it immediately deployable for directive tasks such as entity extraction without any additional training. Using DBRX Instruct as a fine-tuning base is suboptimal because instruction following alignment can interfere with domain adaptation objectives. Using DBRX Base for immediate instruction following deployment produces inconsistent results because it is not trained to respond reliably to prompts structured as direct commands. DBRX Base remains a supported model option in the Foundation Model API. Let's slow down here. The Base versus Instruct choice trips up a lot of people. Imagine 2 engineers starting the same week. One has 50,000 legal case files to train on. The other needs to ship a contract parser by Friday. Same model family, different variants. Here's the fork. Need to fine-tune on your own data? Use DBRX Base. It's pre-trained with no instruction following baked in. That clean slate means your training won't fight existing alignment. Need to follow instructions right now, like extract all party names? Use DBRX Instruct. It's already tuned for commands, so you can deploy it directly. The trap: thinking Instruct is a better fine-tuning base because it's smarter. That alignment actually fights your domain adaptation. Base is the launchpad. Instruct is the ready product. Let us keep moving. Question 18. Ignore details that do not change the decision. A generative AI engineer at Fortbridge Solutions is operating a multi-tenant LLM application serving hundreds of enterprise customers through a single AI gateway endpoint. During a peak period, one large customer sent an uncontrolled burst of requests that degraded latency for all other tenants. The engineer needs to prevent any single customer from monopolizing endpoint capacity while minimizing changes to the application architecture. Which configuration change should they apply? Select 1. Review the answer choices on screen. The correct answer is option B. User-level limits isolate the noisy tenant without touching others. AI Gateway supports rate limiting enforced at the endpoint, user, or group level. Setting user-level rate limits caps the number of queries per minute that any individual customer can issue, directly preventing a single tenant from monopolizing endpoint resources regardless of how aggressively they send requests. Traffic splitting distributes requests proportionally between multiple endpoints and is used for canary releases or A/B testing, not for per-customer fairness enforcement. Inference tables capture request and response data for monitoring and debugging after the fact. They do not throttle or limit incoming traffic. Increasing the concurrency limit raises the ceiling for the entire endpoint equally, which allows the high-volume customer to continue crowding out other tenants at the new higher ceiling, rather than constraining their share of capacity. Let us keep moving. This is question 19. A generative AI engineer at Crestwood Digital is building a content analysis platform that must process both product thumbnail images and short video demonstrations from a catalog. The platform must use a single foundation model API model that natively handles both image and video inputs in a single call, without requiring a separate pre-processing pipeline to extract frames from video. Which model should the engineer select? Select one. Review the answer choices on screen. The correct answer is option D. Only Gemini 2.5 Flash handles video natively. Same principle. Gemini 2.5 Flash natively supports all 4 input modalities: text, image, video, and audio, within the Foundation Model API, making it the only choice that can process both product thumbnail images and short video demonstrations in a single model call, without an external pre-processing step. Claude Sonnet 4 supports text and image inputs within the Foundation Model API, but does not support video as a native input modality, so handling video clips would require a separate frame extraction pipeline outside the model. Llama 4 Maverick supports text and image inputs, but cannot natively process video content within the Foundation Model API without additional pre-processing. BGE Large is an embedding model that produces fixed-dimensional vector representations for retrieval and similarity search. It cannot interpret visual or video content, cannot detect product attributes, and cannot generate any text output. Time for another one. Now for question 20. A generative AI engineer at Dawnview AI is using the Databricks feature store to supply real-time features to a deployed production model. A data governance audit requires a complete map of which upstream delta tables feed into the feature tables that the model consumes. Which Databricks capability provides this lineage automatically without additional instrumentation? Select one. Review the answer choices on screen. The correct answer is option A. Unity Catalog Lineage traces feature tables to source and consumer. Unity Catalog automatically captures end-to-end data lineage for feature store objects, including the upstream delta tables that populate feature tables and the downstream models and serving endpoints that consume them. This lineage is surfaced in the Unity Catalog UI and is queryable via the API without any manual annotation. MLflow Experiment Tracking records training parameters, metrics, and dataset references for individual runs, but does not model the provenance graph between upstream data, feature tables, and deployed models. Inference tables capture individual request and response payloads at serving time, but do not trace how the feature values in those requests were derived from their source tables. Delta Lake Change data feed records write-level audit information at the storage layer, but does not expose semantic lineage between feature tables, their sources, and the models that consume them. 3 takeaways from this session. First, rename or alter an inference table schema and all logging stops silently, with no error raised. Second, hybrid and full-text AI search queries cap at 200 results regardless of index size or matching document count. Third, AI gateway user-level rate limits prevent tenant monopolization. PII detection scrubs sensitive fields before the LLM or logs ever see them. Inference tables fail silently on rename or schema change. No error, just gone. Hybrid AI search hard stops at 200 results. AI gateway enforces per user rate limits and scrubs PII before your model sees it. 3 layers. Know each one.